Hi, can you hear me?
Yes. Yep, we can hear you.
Hi, can you hear me?
Yep, we can hear you.
Hi, can you hear me?
Yes. Yep, we can hear you.
Hi, can
Of
you hear me?
course, and of course, we can hear them.
Yep, we can hear you.
Hi, can you hear me?
Was
Yep,
that
we
an
can
echo?
hear you.
As an echo.
Yep, we
Hi,
can
can
hear
you
you.
hear me?
Of course. Okay, mute mics and let this person figure out their mic situation. Now is the good time. If you would like to test your mic, if you would like to test your screen sharing, we have a few minutes. We are currently live, as we've been having the image up in the background to remind people that unfortunately there's a delay. Fish, of course I was. Yeah, sorry about the echo, folks. We will be starting on the hour. Now is an opportunity for the participants to test their cameras, microphones, and screen sharing, if you would wish to do so. Well,
can you hear me?
Yep, can hear you fine.
Great, okay.
Well, can you hear me? Who?
Yep, we can hear you.
Yep, can hear you, Peter. Really looking forward to seeing your robot. And yes, I would recommend for those in the audience and for those participating, do make sure to share this as well via social media or however you wish. We will see, obviously, after the fact, people watch it in their own time as well, because it is an event that's, across many different time zones for the community. Can I ask, Michael, Chris, have you also done a little bit of promotion in the Discord just to say, hey, live now, happening?
Yeah, I'm about to post that.
Wonderful, wonderful. Done all we can for the subreddit.
I'm in other Discords, not actually in ours.
Yes, please.
Okay, I'll handle ours if you want to do like the controls engineering one or something.
Yeah, I already did.
Cool, perfect.
I would assume everyone in our Discord already knows it's happening, but good to remind
Good to
them.
ping. If we're going to be annoying about something, it might as well be the like one thing a year that we do.
Yeah, for sure.
Perfect. Just a quick thing for the presenters on the call right now. Every section is going to have a question and answer segment. If you would like to ask another presenter a question, obviously that's totally fine, but please type your question in the Zoom chat instead of unmuting yourself to ask it. the team does need to go through and make sure the questions are appropriate and everything before asking them. So if you wouldn't mind, just please post your questions in the Zoom chat instead of unmuting and asking them.
Okay, if you want to do it that way, I'm happy to. I thought we could trust these guys in the chat as long as they're not interrupting each other.
Okay, I'm fine with that too then.
I think. I mean, we've got emails, so we can always yell at you if we have to.
True.
Yes.
Okay, that sounds good.
Yeah. So as long after the presentation's finished in the Q&A session, if you want to just unmute your mic and ask a question, go for it. I'm glad we had that clarification. They're all the same. Hi there, for the folks in the audience, we will be starting in just a few minutes. I will be popping on to give a quick introduction and then we'll be rolling right into our presentations. We've got lots of very exciting stuff, a juggling robot, a soft robot tentacle, some open source servo firmware, and a really good DIY 6-axis robot arm. So I hope to see you in a few minutes. Okay then, hello everyone and welcome. Just checking that I'm not muted. I am not muted, wonderful. Welcome everyone to the third, possibly final Reddit Robotics Showcase, a unique event for members of a global community of all ages and abilities to share their passion and enthusiasm for robotics. You're going to see all kinds of fun projects over the weekend. We've got 4 different sessions, 2 today and 2 tomorrow. Those are robot arms, which we would have been starting now were not for a last-minute cancellation from KUKA. We have at 2 p.m. Eastern Daylight Time, which I believe is 7 p.m. British, social, domestic, and hobbyist robots. Really a great range of exciting robots there. First time we're seeing lots of chat GPT and AI being used on these robots. And then Sunday, tomorrow, from 10 a.m. EDT, we have autonomous mobile robots, including an autonomous sailboat and a giant walking spider covered in flowers. And in the afternoon/evening, we have startups and solutions, again, covering a wide variety of fun projects, including an acrobat and a humanoid, and a recycling company, which is very cool, seeing how robots can be used to make the world a better place in that regard. So we'll be starting off in just a couple of minutes, and I'm happy to hand over a couple of minutes early to Harrison Lowe. All the presenters that you will be seeing are going to have time for their presentation, and then after that, time for a Q&A session. So please make sure to ask any questions you have, no matter how big or small, silly or outrageous, in the chat, and we'll be happy to pass them along afterwards, so long as they're appropriate, but I'm sure they will be. Please feel free to share this event on social media, however you wish, with your friends and family, if you think it's worth it. It's okay. Anyone got any questions for me before we get started? Other than how messy my desk is? No, good. Wonderful. So in that case, if we've got a few minutes, I'm happy for us to start. We'll come back in just a couple of minutes. Harrison, are you ready?
Yeah, I'm ready to go now.
Cool. Well, yeah, if you're ready to go now, I think we can start now, give you an extra couple of minutes, build in a bit of breathing room. It's always nice if someone's willing to go a bit early, it means that someone else can be a bit slower, because everyone's got their own level of skill for this.
Yes.
I will remove the
Let me get backed
spotlight.
up.
And yes. Oh, what motivates us to do this? Thank you for asking. We're all big nerds and we really enjoy robotics, and we enjoy robotics enough to help share that passion with others and support other people with that passion. This event in particular, the Robotics Showcase, this started during the 2020 pandemic, when everyone had all of their events, whether it's conference or Viva or just their score report, it was all cancelled. And so we started doing an online showcase for all ages and abilities. And now we're also, able to get lots of people from industry and academia to participate as well. So it's really nice to see a wide mix of projects. With that, I will hand over to the start of our fantastic session on robot arms of all different kinds with Harrison Lowe and a juggling robot.
Awesome. Cool. So this is my project Deep Blue Juggling. And before we get into what the actual robot itself is, it's probably worth answering the question that I imagine is probably on some people's minds, which is, why am I even doing this? And the long story short is that I've been juggling for a bit over 10 years. I studied mechanical engineering at university. I got about a year and a half into doing a PhD on haptic feedback, and then COVID and a bunch of other things happened. And I decided that it would be more interesting to spend my time building a juggling robot. To understand the robot itself, I think it's useful to break it down into 4 main subsystems that roughly correspond to systems that humans use to juggle. And these are the arm, that is responsible for the large, gross movements, the hand, which is responsible for the actual catching and the throwing of the ball. Once the ball is thrown, you need eyes to see where the ball is. And then to actually get the whole thing moving, you need a brain. So let's have a look at all of these in a little bit more detail now. First up is the arm. And something that was really helpful with figuring out some design requirements for this component is that while I was in uni, I did a course that was based on biomechanics. And I got some motion tracking data of me juggling, which has been very nice because it's let me put together some plots of, for example, how far my wrist moves doing different numbers of balls. But to actually break this down further into what the arm itself needs to do, I'm going to propose that we get rid of the Z component, the vertical up and down. That will make a little bit more sense later once we understand how the hand works. But as far as the arm is concerned, we only really care about left and right and forwards and backward movements. And for a couple of reasons, but they don't really matter too much, I decided that 5 balls was a good sort of goal number to be able to do. And that gave me a limit of 0.3 meters in the X and Y direction that the robot needs to be able to cover so that it can juggle the way that I juggle without the balls colliding with each other in the air. Now, some other data that I got from this experiment, or this tracking data, was the frequency, the rate at which balls were being thrown. And this is really useful because it informs how fast the robot needs to be able to move around to catch and throw the balls fast enough so they don't collide with each other. And again, 5 balls is a good sort of rough baseline, and that gives us a frequency of 2 hertz. So that means that there are two throws happening every single second, which means it needs to go from the throwing position to the catching position and back again 2 times every single second, meaning that the robot needs to move at least 1.2 meters per second. Not only that, it has to also be precise and move in at least 3 degrees of freedom to be able to throw the ball properly. After a bit of umming and ahhing, I came up with the design of a 6-degree freedom parallel mechanism, which is often called a Stewart platform. And this image here was from Wikipedia of these Stewart platforms. And I've spent a lot of time looking at that GIF. Quite like it. And this is good, but it raised a couple more questions of what geometry do I actually want to use for this platform and how do I want to actuate it? For the first of these questions, I made a simulation that essentially plotted a ton of points in a volume and moved the upper part of the platform around. And for every point, it checked if all of the legs of the actuator, if all of the legs of the robot, which are, oops, if this lets me draw, these guys here, it checks to make sure that they are all within their allowable length ranges. And if they are, then it plots the point as being green and it is deemed reachable. If one of the legs is either too long or too short, then it is unreachable and it's one of these red points. Now this is good, but it doesn't really allow me to check different geometries very quickly and easily. Importantly, what I was interested in is what angle should I have between the nodes down here and what angle should I have between the nodes up the top? And also, how big should the base be compared to how big the top is? I didn't really know what this should be. I could have looked at what this diagram was telling me from Wikipedia, but I didn't because I'm a fool. But I wanted to know for myself what they would actually, like what would be the best. And so I made a simulation that just ran this thousands and thousands of times. I can't remember the exact numbers off the top of my head now, but this took like 2 days to run and it was pretty nuts. And what this told me is that all of the angles should be 60 degrees and that the base and the platform should be the exact same size. And this will give the largest reach rate. I thought, cool, this is great. Let's see what that actually looks like. Straight away, I thought, wow, that's awesome. This has like 4 times as much reach rate as this other one that I had. So this should be great. So then I built it and it was extremely unstable because I did not include stability in my criteria that I was checking against. So what I did is I basically just scrapped all of this and did what Wikipedia was telling me to do and made the nodes as close to each other as possible. And the 2 radii, the base radius and the platform radius, made them the same. So that's the geometry done, but now I needed to know how to actually actuate the robot. And what I did for this is, it's a bit of a long story. My first design involved syringes and was clunky at best. It was, kind of questionable. My second design used some store-bought linear actuators that I got off of AliExpress, And this was cool, but they were really weak and really slow. My next design used some ball screws that I put together, some stepper motors with ball screws. They were also very slow, but they were super, super strong. And that was really satisfying getting that working. I had a bit of a dark period after that. Once I realized that was too slow, I tried a lot of different things, some more questionable than others, before I landed on this design, which used strings to actuate the legs up and down. This, after a little bit more improvement, took me to my current design for the actuators, which involves a 150 kV brushless DC motor that is collinear with the extension axis. The motor is this, you can just see the R of the label there, that's the motor, this black bit down here. There are two strings, one acts to extend the actuator and one compresses the actuator. And each string has 3 pulleys to route it around in its correct path. I think this design looks really cool, but of course, looks are not everything. So we need to know how well it performs. And my last design, which was very similar to this, it shares a lot of components the same as what this design does, was able to reach 2.6 meters per second. And this shitty prototype that I made for this new design lasted 39,000 cycles before one of the strings broke. Thankfully, it broke in a way that is relatively easy to fix. And for my next prototype, that should be resolved. And I expect it should be able to last a lot longer. I'm just waiting on some carbon fiber tubes to be able to make a proper prototype for this. Once that's made, I plan on testing or measuring the power by fixing a mass to the end of the actuator. And we can calculate power by force times velocity, where force is the mass times the acceleration. So that should let me calculate the maximum power and the average power and all this sort of stuff of the actuator. I also plan on measuring the precision by moving it to a known position, measuring exactly where it is with my calipers, moving it around a bit, returning it back to where it was before, and seeing if it actually is where it was, or where it's supposed to be. I'm very interested in this one because precision is quite important for juggling. So we'll see. So 6 of those go together to form the Stewart platform of the arm of Jugglebot. And now let's have a look at the hand. The first thing we need to do is figure out what the design requirements of this component are. And this component needs to have a very solid grasp of the ball during the hold. If it is not grasping the ball really solidly, then it will slip and the whole thing will fall apart. It also, of course, needs to catch and throw the ball. But how high? Well, I turned to this very interesting book called The Mathematics of Juggling. And in this book, there's a table of how high throws need to be made to basically not have collisions, and if the throws are being made at a certain rate. And again, 5 balls, good benchmark. So I just said at least a meter high. I think if humans can do it at 1.2 meters, a robot should be fine at 1 meter. And with some very basic math, we can figure out that this means the ball needs to be thrown at 4.4 meters per second. Similar to the arm, there were quite a few iterations on the hand. I actually don't have footage of all of the designs that I made, but the first design that I do have footage of is this one that had this sort of like lobed cams to launch the ball up. Now, this obviously doesn't have a very solid grasp of the ball while it's being held. It's just very tenuously held in there, but it did do a decent job of throwing. There are a couple issues with it though, and so I changed the design to this that involved this like cup part in the middle, moving up and down, guided by 3 rails. And this cup part would be pulled up and down by a string that ties on down here and goes up over these pulleys. And that design was good. I'm glad that I did it, but it wasn't the best. I then had a bit of a foray into compliant mechanisms, and that was fun, but not the most relevant for this project, I soon found out. And that finally took me onto the precursor to my current design, which works really, really well. I'm constantly surprised by this. It's really cool. The way that this works is we have strings that are shown here in green that are routed from the base of the robot to the base of the hand. And as the arm moves around, these strings are pulled, raising this central cuff part. And then these these springs, which are shown here in pink, act to pull the cup part back to the hand, back to like the base of the hand. I think this is probably easiest to just show you in with my current one here, that this actually does work. It's really neat. If I just pull this string here, it pulls that cup part up, launching the ball. Super smooth, super satisfying. I'm a big fan of it. That's how the hand works. And now let's have a look at the eyes. The design requirements of the eyes. I'm a little less certain of any of these because I don't have any experience doing any computer vision stuff, but I knew that it needed to track the balls as quickly as possible, as precisely as possible. Cheaper is good because I'm not made of money. And I would also like it to be portable because I want to be able to move Jugglebot around into different places and juggle in different environments. I think would be cool. I'd also really like if it was compatible with standard juggling balls so that I can just like juggle with it, with like me and it, performance together. I think would be kind of neat. And these are my main sort of criteria that I was comparing my different eye options. And to have a look at what some of those were, the first one was the OptiTrack system, which for anyone who's unfamiliar with it is basically like the gold standard of motion tracking systems in like entertainment industry and everything. It's nuts. It is obviously extremely fast, extremely precise, and extremely expensive, as well as not really being portable and not really being compatible. I would have to move all of these cameras around to the space that Jugglebot is acting in. And I don't have any experience with any of these systems really, but I would guess that I would have to either use custom balls or like spray paint balls with like retroreflective paint or something. It wouldn't be just a drop in with normal juggling balls. The next one that I considered was using these Tundra trackers with the Steam VR lighthouses. And so these are little trackers that are used for VR. I think people use them for like body tracking in VR. And these systems this is quite fast. I think it can do around 100 hertz. It's fairly precise. It's not as precise as the OptiTrack, but it's pretty good. The cost it's kind of expensive. I think it's a couple $100 for each of the trackers as well as the lighthouse. But I already own them, so that's not too bad. It's somewhat portable because the lighthouses are relatively easy to move around. But again, it's not really compatible because the way that this would work is I would print a sort of Voronoi ball that the tracker would go inside, and that way the camera can still, or the lighthouses can still see it through these holes, and it still retains a ball shape. So that would be extremely custom balls, and I don't know, that would be a bit of work, I think, to get the tracker to be in here without interfering with the tracking itself. So that's a not hugely compatible design. And the final design, well, the final product that I was contemplating is these OAK-D light depth cameras. These are sort of fast. They should be able to do 120 hertz if everything's set up properly. I have no idea how precise I should expect them to be. I'm going to guess less precise than the other ones. They are the cheapest, and I already own some. And they are the most portable and the most compatible because it's all just working with computer vision. So it doesn't, like I can just use normal balls. I can just teach it or calibrate it to use normal juggling balls. And this is my favorite of the three options, and that's what I'm moving forward with. And this is what it looks like right now. So this sort of blue, transparent or translucent volume is the field of view of the camera, which you can see is mounted down here. And this is what it looks like when it is tracking. For some reason, PowerPoint has really kind of throttled all of my GIFs, so you can't really see this very well here. But the way that this is working is it's applying a filter on the HSV stream in this image here, fitting a circle to that mask, and then finding the depth data from that circle, like the average depth of that circle. I do need to do a bit more testing just to see if this is working properly and to try to speed it up a bit, but it looks like it's working relatively well to me so far. So that's how the eyes work. Now let's have a look at the brain. Now, the high-level overview of what the brain needs to do is it needs to take the data from the eyes and tell the arm where to go and when to go there. I see that there's two ways to do this. There's the old school way, involving hard coding everything, which would involve, for my purposes, an occipital cortex, if you'll allow some more biological analogies, whose job it is to get the true position of the ball, because any sensor tracking is not going to be perfectly correct. So this wants to get, well, the job of the occipital cortex is to figure out exactly where the ball actually is. We then have a frontal cortex, whose job it is to create a path for the hand and the arm to follow, to make sure that it can be where it needs to be at the right time to then either catch or throw the next ball. And there's a motor cortex that actually commands the robot itself to move around. That's the old school way. I think it's relatively likely that at some point I will try option 2, which is just to get AI to do all of this. And I'll go into that a little bit. I'll go into that in more detail in just a sec. The way that I have the occipital cortex working is that it's taking in the noisy tracking data from the eyes, applying a Kalman filter, which basically combines what should be happening based on the known launch, like throw position and velocity, combines that with the observed noisy data from the eyes. And it combines those to predict what the landing position should be. And you can see it works pretty well, I think. And as the more data comes in, it's more able to calibrate to a approximately correct landing position. And if you're interested, this simulation was run with up to 10 centimeters of noise for each data point, which is pretty big in my mind. I really hope that the depth cameras can be more precise than 10 centimeters. That's a lot of noise. It's also going at 100 frames per second, and the launch velocity is incorrect by 0.1 meters per second in the X and Y direction. So I think that overall the Kalman filter is doing quite a good job at accommodating for those inaccuracies, and it gets pretty close at the end. The frontal cortex, its job is to take in where the ball should be landing or where it should be thrown from, as well as the velocity of the catch or the throw. And also takes in the status of the hand, whether it is currently holding a ball or currently empty, as well as the hand's position. And then it figures out what the hand needs to do next. And this was actually a lot trickier than I was expecting it to be, because something that's really, really important with juggling is that all of the catches and throws are really smooth. Everything has to be smooth. If there's any jagged, abrupt catch or anything, then it's not going to work. It needs to be very, very smooth. And so the way that I did this is using 4-point Bezier curves. So the hold path and the empty path are made by these 4-point Bezier curves, which ensure tangency with the incoming or outgoing ball. And finally, we have the motor cortex, whose job it is basically just to tell the motors what to do. This is definitely the simplest one. I'm using 3 ODrive V3.6s, and I hope that they will be able to update the position of the motor at 1 kilohertz. I've never done anything like this before, so I don't know what speed to use. I just heard that Boston Dynamics does 1 kilohertz, so I'm gonna lead from their example and try to do that. Now, that's if I was doing everything the traditional way. I think it would be cool to do AI stuff. And what I would probably do with that is using NVIDIA Isaac Gym, just because I've seen the most about that. I know there are other options, and I'd be very interested to learn if there would be anything more appropriate. But this seems like a pretty set up system. And hopefully, if I can get one, I would love to use an NVIDIA Jetson or a Nano, because these things seem absolutely nuts for what they can do. But we'll see. The next few steps for the project are to calibrate my depth cameras, just to make sure that they are actually correct, to build and test the new linear actuators, because I need to make sure that they work. And as soon as I get my carbon fiber tubes, I'll be building them. I need to solve a CAN issue because my CAN system is not working. And I would love, if anyone is familiar with CAN, hit me up. Yeah, I'm having problems with that, but I think it should be okay. And I don't really know what else. Some other things will probably come after this, but eventually it should be able to juggle, hopefully soon. 2 long-term goals for the project. One is to beat the world record for ball juggling, which is 14 balls and 14 catches, which is absolutely nuts. I have no idea how this guy can do this. It's insane. And the other one is to get a troop of jugglebots, a whole collection of them, all juggling together with LED or glowing balls in time to music with a drone flying through. I think this would be absolutely insane, like the Tesla factory style drone thing flying through, have it all choreographed. I think that'd be absolutely nuts. And that's it. So thank you for watching, and I am open to any questions that you've got.
Oh, that was fantastic.
Yeah, that was really great.
Personally, I always get nervous about these events, and in the run-up to it, thinking, "Oh, is the effort and the time I put into it worth it? Am I going to enjoy it?" And then, as soon as the presentations start, that's a really good one to start on as well. That was really cool. Great presentation. My PhD is related to compliance actuators. There was a lot of stuff I found very interesting there too. You've got compliments for the quality of your Kalman feature as well. And yeah, there's lots of interesting questions about the vision stuff as well. I really, really like the idea, the long-term goals you have. The idea of getting multiple to juggle together. I will let
I think it's
Michael
going to be awesome.
ask a couple of questions from the chat, if that's okay.
Yeah, absolutely. You got it. So our first question is about the tension on the actuators, on the strings for the actuators. So how do you keep tension on the strings for the actuators? And specifically for the catch throw actuator, how do you keep tension on that while it's, moving around in 6 degrees of freedom all the time?
That is a good question. So I'll answer. I'll talk about the hand first. So this guy, the hand, I have the string, I will have the string set up so that it is like tight at when the jugglebot is like at the bottom. Mm-hmm. And then, so it can only ever go up, basically. It will never become more slack on this string. It will mean that will almost certainly limit how far the arm can move around, because this will like hit its length limit before the rest of the robot will. So that will put a bit more of an imposition on the range of motion of the whole robot, but I think it should be okay. And I've got a couple of ideas of like gearing this down to accommodate for that. But yeah, it's essentially, it can't become more slack. And just to answer for keeping the strings tight in general, I don't have one tied onto here currently, but the way that I'm like fixing them onto the end is the string goes through a little hole and I wrap it around. It's not focusing. There's a little bolt there. So the string passes through. There's a small hole, if I can get it to show, right next to the bolt. And basically the string comes up, wraps around the bolt, and then I just tie the bolt, or like tighten the bolt in, and it will like clamp it up. So if anything does get loose, it's just loosen the bolt, pull the string, tighten the bolt back up again. And it's really quick.
Okay. Very cool. Someone asked, you base your assumptions on the speeds and heights of the balls on, your motion capture for human juggling. Do you expect that that's going to be the optimal value for a robot juggling, or do you think there's something different about robots juggling that might cause those values to be different?
I think it is a conservative guess. I think that the robot will be better. I think the only reason, it's like when you see someone do something really well, you think, wow, that looks effortless. It looks like they're not doing anything. And when you really get like in the zone and you're juggling, it's really no effort at all. You just keep it going, just keep it smooth. And I think a big part of the reason why humans find such a hard time with juggling is that we just can't do things that consistently, but robots can, in my understanding. So I think that it will be more, it will have a tighter pattern, and I think it will be able to like shrink those limits down a lot. So I think that what I've based all this on, like the 0.3 meters XY, all of this stuff, I think is very conservative. Yeah. I think if you can do those range of motion and that speed and everything, then it should very easily be able to juggle better than I can.
That's very interesting.
Can I ask a question?
Please go ahead.
Yeah.
I really liked the whole way you've approached the project is really good, frankly. I like the way you've gone about the not AI route first, because it means that you're going to have lots of really reliable data and solutions that work and how well they work. And rather than asking your AI, it will magically solve everything.
Yeah, the black box.
Target this is the problem I can't solve, but these are reliable data I can use to develop a solution for. Yeah, I can very much see some reinforcement learning going a long way there to juggling. And the nice thing, you've got simulations too. So you can do a lot of the work in simulation for very little money before you commit to buying.
Oh, I think we lost you for a second, Ollie.
Yeah. But I do agree. It would be good to be able to test things in sim before buying them.
Yeah.
Yeah,
absolutely.
my wallet is not loving this project.
Yeah, that is the unfortunate reality of self-funded work, huh?
Yeah.
Yeah. But we have one more question from the YouTube chat, which is, someone said they noticed online that you sometimes refer to the Jugglebot as the, first real or the first proper juggling robot. Now, how do you consider your robot to be different from the other juggling solutions out there?
Yeah, that's a very good question. So there's a really good video by Luke Barrage that I'll post in the comments when I'm done with this, where it's basically like a literature review for this project, and he released it like 6 months before I started on this. It was such good timing. I'm like, wow, like yeah, it was great. But he describes juggling automaton and juggling robots as being separate things, where the automaton are things that are hard coded, and there have been a lot of these that people have made. I think Claude Shannon made the first one, where it's just a mechanism that follows a very predetermined path, and like a person has to load the balls in at the right time, and if it drops, it just keeps on carrying on, happy as Larry. It's got no idea. That's obviously not going to be able to do what I want it to do. So I need to be a juggling robot where it can actually sense the balls and accommodate for where the balls actually are. And I'm only familiar with one example of a robot that does this, and it's pretty not great. I am fairly confident the people who worked on that are not jugglers themselves. And I think that they just made like arms and a human sort of hand, and they just wanted to like show off what it could do. And so they made it juggle 3 balls, and it was, it's not great. So yeah, I think that this will be the first robot that can actually juggle the way that it can make the balls move the way that humans can make the balls move. Maybe the way that the robot is doing it is quite different to the way the humans do it. But yeah, I think that's where I'm coming at it from.
That's a good definition of that. Yeah.
There's a question from the chat. It's definitely a more long-term goal for you, but when you get it, outdoors, I suppose, do you have any thoughts about how you would account for wind?
Wind is an interesting one.
It's indoor juggling robots.
I don't really think wind is that big of a problem, to be honest. Not with ball juggling. I think this is why I have sort of steered towards ball juggling. Like I used to juggle rings and clubs and stuff as well, but with both of those, if it's a little bit of wind, they just blow away. But the balls are like, they're fairly dense and they're fairly small, so they don't really get it. Like unless you're in like a hurricane or something, it's pretty fine. And I think with the Kalman filter approach and that sort of thing, I think it should be able to accommodate it pretty well. Or unless if it's throwing like super, super high, maybe that guy that got the world record would have a different opinion on wind to me. But
yeah, breaking the record might require some compensation, but just getting it juggling, you're right. The density of the ball,
I think it should be fine.
Yeah. There's definitely a range, a working performance range, and then beyond that height, it starts to get more of a factor.
And also even with the way that the hands are now, like the space to catch the ball is quite big. Like the ball can very easily fit in there. Like it's got a fair bit of room to mess up. So yeah, I think it'll be okay. I'll have to see.
Yeah. Someone asks, do you have any plans to make it do any other tricks, like varying the path that it's throwing or changing the number of balls on the fly?
Yeah. Something that I would really like it to be able to do is to juggle. It's a little bit, just before I answer that, there's a thing that is used to describe juggling patterns. It's called site swap notation, where you can basically encode the pattern with numbers. So for example, this pattern that I did right at the start with me juggling has a pattern of 6x4, 4, 6x. It's a bit of a weird number, if I can get all the way back there. That one. So that's got a very specific number, and that's the only way that that pattern is described is with a number. I don't think it has any actual name other than that. And what I would really like to be able to do is tell Jugglebot to start doing this pattern, and then it can find the path to get to that pattern, and then go into that pattern. There's a lot of stuff involved with that. It's kind of hard to describe. But yes, that is a goal that I would very much like Jugglebot to be able to do, is basically say, do this, and then it will figure out how to get there, and then it will do it. I think that would be very, very cool.
It sounds like a great goal. Yeah.
Yeah, thank you very much, Harrison. Yeah, delightful way to start.
Thank you.
And with that, we're going to hand over to the next presentation, which I'm going to say Jan, not Jan, and is here to talk about open source servo firmware, which is, again, I'm interested to see what you have to say about that. So when you're ready, I'm going to pin.
Hi, I'm Veverak. First, small warning, I am on outside retreat, and there is a big church behind me. So it might ring at certain moments, so just fair warning about that.
We can't see your screen. If you might.
Yes, I'm not yet sharing it.
Okay,
I'm just on my way to do that now. And here we go. So first I will give you small background about me. I am computer scientist. I am software engineer. I don't have much knowledge in control theory except what I learned recently or with the project I'm going to present. So just keep that in mind and have some patience with me about the control stuff. And let's move on. So some introduction. What I'm working on is open source firmware for servo motors, something like ODrive, but the key difference is that we are working on something that can control traditional DC motors, because we still think that they are still usable and we have some specific use cases for them. What exactly that means? There is a GitHub repository, there is a firmware. It was not yet presented. This is actually the first time somebody except for us saw the project. And the idea is having open source firmware for control of small DC motors. And we are talking about project that uses C++20 and STM32 microprocessors. Sorry. Why? Which I think is the most important question. Me and friend of mine, we always wanted proper servo motors for our robotics projects. What you can see on the pictures is my diploma thesis, which was attempt to make software for electric robot. And we kind of always struggled with that because we either had RC servo motors, like the traditional hobby motors to cars or planes, or expensive industrial motors. Industrial motors were a problem for us because they are expensive. And RC servos, they lack the necessary feedback because, with robotics, we kind of want to know what is the position of the servo, how much current it's flowing through the servo and stuff like that. So we got the obvious idea, hey, how about building our own? We can do it. It's simple, right? The vision was to make open source firmware first, as a secondary product, make some PCB designs that can work with the firmware. And the expected use case with which we started was that, let's buy RC servo, throw away the electronics that was in the servo, and install our own. So we can use existing mechanics component, but use our own electronics and mostly firmware. What you can see on the picture is the common hobby servo from AliExpress, which I like to use for testing. Unexpected use case that we find out after a year or year and a half of development is that, wait, we don't really need the servo either. We just can take any DC motor, connect it to something, slap somewhere potentiometer, and tada, we have 40 servo motor. And that idea kind of grew a lot, and it's one of the second focus of the project, that this is the use case that we want to support. On the picture, there's just prototype design of one of my robotic arms in which I kind of want differential movement. And I really love the idea that I can insert the encoders into the gears and have motors somewhere else with belt drive. And as something maybe unexpected, I put a lot of focus on testing infrastructure. I have a lot of tests. And we kind of want to keep that closed source because there was the idea, well, we want to make open source project, but we need to put time into it, and that takes some resources. Is there some way with which we can make this into something that makes money for itself? And the idea that occurred to me, hey, we can make open source firmware and just say, well, if you want extensive testing infrastructure, write to us, we can sell you something as some way to make money. So what's the stage of the project? Current goal is just to reach version 1, which represents minimal viable product. It has basic capabilities, position, current, and velocity control. We already implemented, tested, and finished a lot of capabilities like current sensing at high frequency, speed control loops. We have working limits for the movement of the servos and other aspects, but we are not there yet. What remains is make black box testing, persistent configuration testing, switch to protobuf interface. So there is still a few steps to finish, but it's not that much. After we finish the first version, so we are getting close, we want to use that project in something that's called Robotarna in my native tongue. And it's a group of people that are teaching robotics to middle school students. We have a lot of lectures for them, a lot of fun for the students. So we want to use the servo motor there. So that's for the introduction. Now about some interesting details about the project. I will go through components, PCB, velocity control, tests, and some extra information. From the perspective of components, as what composes the project together, the core element is the firmware itself. We also, or at least I, as a software engineer, put a lot of focus on the interfacing of the servo. That is, how will users be able to communicate with the servo motor? Part of the project is my personal C++20 library for embedded development, which I'm using heavily. We have open source design of PCB, which is not yet published because of lack of time, and extensive testing infrastructure that allows me to develop this and have some long-term maintenance of the project. The PCB itself at this moment is quite big. We are at 35 millimeters. This will improve in the future. This is just a prototype, and to have easier debugging of the project, so I can actually attach my oscilloscope to it, we make the PCB quite big. This can be much smaller, and the two main components on the board is the MCU, STM32G4, and our H-bridge, which is the DRV887. And one remark about that, we did not want this component, but when we designed this version of the board, there was still a lack of components, so we took whatever was available. So how does it work inside? I mean, based on some feedback from people that actually work in industry with these systems, we got the hint that we can have sequence control loops. That means that we have three main control loops. Each can control or execute one type of a command, and they are chained together in a row. That means that when we want to control current, the current control loop is the only one that can actually interact with the motor itself via the H-bridge. And only thing that it does is that it gets current measurements, that is how much current is going to the motor, and based on that, it regulates duty cycle of the PWM pulse. That way we have current control. On top of that, we have built it velocity control, that is, we are measuring position of the servo motor, making some velocity estimations with Kalman filter, and we are feeding that into velocity control that regulates current that goes to the motor. And on top of that, we have position control. These three control loops kind of represent what we want to achieve in the first version, and that is commands like go to position, maintain velocity, and maintain certain current that goes to the motor. Now to the tests. As a software engineer, I like unit tests, and I like them a lot. So I kind of developed my own testing framework. And what it means is that I can just write make basic test in my terminal, and the command will compile testing firmware, flash it to the device, run host application that can actually tell the firmware to execute the test, collect data from the test, and evaluate them. And this was extremely powerful because it simplified the debugging of the MCU a lot. And today, every time I make a change to the firmware, I just write make tests. It takes a while, but then I see all green and I'm happy because everything works. We have 3 sets of tests. The basic tests just tell us whenever the servo is functioning correctly, that is whenever all peripherals are configured correctly, whenever everything is executed. Just basic sanity checking, but this is already proved to be a good investment. We have benchmarks, which are not actually testing functionality, but telling us what the servo can do at the moment. So this way, I can periodically check that our main control loop for the current control is running at least at 10 kilohertz, as you can see on the picture. Or one of the benchmarks that I have is how much time, most probably, I'm spending in interrupts versus the main control loop of the servo motor, which was quite helpful for debugging and analysis of the system. And as a third set, I have to switch, is the one that I like the most. We have this set of scenarios that represent simple command for the servo, like go to certain position or go with the current up and down. These tests are sent to the servo, it executes the movement, and during the movement, we are measuring position, velocity, current, power, and collect the data back. After that is done, I get this nice report about how well the servo is behaving. And when we go into more detail, I'm using this model interface for analysis of the system to see in details how the values look like. And I have to say, this saved a lot of time and allowed me actually to fine-tune the PID control loops and make them work. There are other implementation details that might be interesting. Communication will work over half duplex quad, which is somehow standard. We want to use COPS as a framing mechanism and protobuf messages as the content of the messages. We have full limits, or our PID control loops have limits that are respected at all times. We have rich configuration capabilities, especially ability to set up the PID parameters. Eventually, I will make some of the tests open source, but the most advanced tests, I kind of want to keep private at the small chance that somebody actually would want them, and hence we would be able to support the project with that way. And obviously, we want various host utilities, like for example, store or load configuration. So what will happen now? V1 might be finished like in 1 month of my after the work free time. However, that was quite limited lately, so I'm expecting something from 1 to 6 months. That's the best guess I can make. And as for V2 or what we plan in the future, back from the basics, I want to add proper documentation for the repository. I want to support traditional encoders or magnetic encoders, as that we are not able to do so yet. We want to make small PCB. Actually, we want to make as small PCB as possible, as that would be kind of cool. We want to support continuous mode, and we want to implement motion planning. And as the last problem that I will find the most challenging, I think, synchronous movement of multiple servo motors in real time, as that can be quite challenging. And to finish the talk and actually switch to something that's quite interesting for me, what kind of functionalities you would wish in open source servo for DC motors? Like, what would you want? I'm kind of interested for that answer from community, as it might help us steer the good project.
Okay, very interesting. Also, the next the next presentation we have scheduled hasn't turned up. So unless they turn up in the next couple of minutes, what we'll do is we'll extend the question and answer session for you, and then we'll let Peter go straight into his presentation as well, give them an extra few minutes, which I'm sure will be worth it. Yeah, Michael, could you ask a couple of questions then, please?
Absolutely, yes. We have a few questions from the YouTube chat. So what is the goal of your project more to teach about servos with more of a hobbyist audience, or are you trying to create a product that you think is missing in industry and sell this to people that are using servos for industrial applications?
Yeah, that's actually what we are not, or the area in which we not decided yet. The end goal is to support our needs that we had as, well, basically children, where we were not able to afford proper robotic servo motors. So we want there to be an option to buy open source electronics that's at a reasonable price, and we want to achieve that. If in the meantime we will be able to make something that's interesting for the industry, that would also work out, and we will be happy about that. But it's not the primary goal. It's like secondary goal that we don't want to give up yet.
Okay, great. Yeah, no, my first thought when seeing this project was, I'm sure I'm not the only person who's been frustrated by how limited off-the-shelf servos are. I mean, they're just, they never really quite do what you want out of them, right? So it's very interesting to see this kind of project. Do you think you might add something like direct torque control in the future? Like if we want to have the motor, execute some certain amount of force instead of a position or velocity, do you think you guys would support that?
We kind of wanted to do that in the first version. We were already thinking about it.
Okay.
But it became quite a challenge for various reasons. And at certain point in time, I made the decision that current control is enough, because you have linear dependency between torque and current. And it's much easier to make just current control from the perspective of software development. And I kind of wanted to avoid the pitfall that you are making a hobby project, you are too creative with what it can do, and suddenly you create such a huge amount of requirements that you won't be able to finish it.
Okay. Yeah. No, I like that. I like the mentality. I gotta say,
I learned it the hard way, obviously. So.
Yeah, no, absolutely. I also want to say it's rare to see such a hardware-focused project with such really fantastic unit testing. It's always like fun to see really great, clean unit testing on projects like this. So yeah, thank you for sharing.
Which really makes a difference when someone is considering actually using your work. If I'm going to copy someone's open source hardware, knowing that it's been tested to that standard means I'll actually want to use it, rather than saying, "Oh, it works on my end." Like, cool.
Very glad it works on your end. Thanks.
Cool. Yeah, on the other hand, to be clear, I have seen as a software developer that tests worked on one machine quite well, and once you executed somewhere else, it stopped work. So as much as I like my tests, I'm not jumping in AV yet myself, because still a long road to rock and roll.
Yeah, absolutely. Okay, well, I think that's all the questions that we have from the chat. So
can I just make, before we hand over to the next one, sorry, Michael.
Please go ahead. Yeah.
My suggestion would be, once you think you've got a prototype that you're ready to share, you should consider either having a look within the the hobbyist community or academics at universities to see if you could send a couple of the PCBs out and get them being used in robotics applications. That would be a very good next step, because then you'll get that feedback and that testing and more publicity for it and all those good things.
I'm teaching basic embedded course at the university, so that's already on my to-do list because I am the teacher, so I can do it.
Perfect.
Wonderful stuff then.
Even built-in testing audience. Wonderful. Yeah.
Okay, back to you, Michael. I'll let you do the transition.
Yeah, of course. So with that, if Peter's ready to go, then we'll just jump right into Peter's presentation. We are skipping, unfortunately, one of our presenters who is not currently on the call, but if they show up late, that's fine. We'll just fit them in after Peter, and if not, then we'll just take our lunch break and break until the afternoon session. So Peter, if you're ready, go ahead and take it away.
Yeah, hi guys. I hope you can see my presentation. Is it up?
Yep, we can see it great.
So, hi, my name is Petar Czerniak, and I'm gonna make a presentation about the CM6 robotic arm, but it will transition from previous project to future projects. So it will not only be about CM6, but it will be interesting. So something about me. I've been doing this for 5 years, building robotic arms. Most my academic career, I have master's degree in robotics, and some main focus of my projects is to create robots that can be used in education, research, and small automation industry, and to make transition 3D printers became more popular. I want to do that same thing for robotic arms and generally robotics, so make it affordable and available to everybody. And I'm kind of making it some plans to make as much as I can open source or just affordable in price. So how the journey started is with the phase 4 robotic arm. I hope the video will load. So some stats about it. It is a 6-axis robotic arm. It uses stepper motors, open loop, so homing is with limit switches and inductive sensors. I believe it is one of the first robotic arms that used cycloidal 3D printed cycloidal gearboxes, and the belt drives. So only the last joint, so the joint 6 uses a planetary gearbox that is off-the-shelf component. So it is a bit older project, I believe 4 years now, and I'm not currently really developing it anymore, but it is fully open source and there is a bunch of community builds. And the interesting fact is that most people build it better than I did, so I guess the instructions are good. Some stats also, it has payload of 1.5 kilograms. Repeatability and precision depends on how tight you print the cycloidal gearboxes, and it is being used by a few startups for research and development and stuff like that. So I was not really happy with this robotic arm because mostly it was just huge. It weighs 15 kilograms, and recently one person contacted me and told me that he wanted to print this arm. And after reading the instructions and slicing all the STL files, he said hey, I need 3 weeks to print this. And I said, yeah, sorry. So yeah, also the robot has quite active community. Some users ported the robot to ROS. For the previous video, I used MATLAB robotic toolbox. There's also a Unity simulation, and for most of my projects I'm using or MATLAB robotic toolbox or Python robotic toolbox made by Professor Peter Cork, and that is like only thing I use for control and simulation. I believe that is like one of the best simulators and on the market, and it's open source. So after that, I created the CM6 robotic arm. So as you can see, it's much faster, and it's not as clean as Phase 4, but it has its charms. Also, it doesn't use cycloidal gearboxes, but planetary gearboxes, and the actuators are actually QDD, so they're low reduction systems ranging from like 6:1 to 10:1, and I believe it's like second robotic arm like this. The first one was Blue robotic arm from Berkeley University, and this arm was really inspired by it. It has payload of 2 kilograms and much lower weight, so like 6 kilograms, and it is also fully open source. So yeah, here is also one built from the users, where he did a better job than me with cable management again. So, was to make like user-friendly GUI and interface. I used the Kinter to make most of the graphical stuff, and it's made on Python, of course, and the multi-processing module. So one process is running the Kinter GUI, the other process is running some complex kinematics and stuff like that, and the other process is running communication stack, and that worked pretty well. So the actuators, they were also made like to be really modular, so you can stack a few stages of planetary reductions to create a much larger reductions, but I didn't really use it, but everything is open source, so people can play around with that. And so about the controllers, they were called S-Drive, and they were made to drive those BLDC gimbal motors, and they actually worked pretty well. But I didn't, at the time I was making them, I didn't really know proper FOTS control, and I kind of messed that up, but it still worked, but I was not really happy with it. And it was supposed to be like daisy chainable, but I scrapped that idea because I was not happy with the fact that it cannot run FOTS. So I kind of moved to the next stage. So these controllers were made from the S-Drive. So we have a FOTS stepper controller that can run FOTS for stepper motors, and a spectral controller that can run that is similar to S-Drive but can drive so it has current sensing and can run FOTS, has a CAN bus, daisy chainable, and everything like industry standard stuff. So like the Jugglebot presentation said, 1 kilohertz update rate that is being used with Boston Dynamic robots and I don't know, Mini Cheetah. And that is it. It also both boards have magnetic encoders on the bottom side, so the resolution is, I believe, 14-bit. the standard. So both those previous arms, I decided to make a new one that kind of builds on best from the both previous arms. So it still uses stepper motors, but it is much smaller. I scrapped the plastic gearboxes because they were too unprecise, and I went with off-the-shelf planetary, high-precision planetary gearboxes. And so this is that new arm, Parole 6. And the cool thing here is that it is much smaller than previous arms. It has only reach of 380 millimeters, while the previous have like 580, 600 millimeters, so like a normal human arm. The cool thing here is that it also has pneumatic tubes running through the arm, so you can easily attach grippers. And also good thing is that with the previous drivers like that fourth stepper controller, you can just attach those drivers easily on the steppers and have a closed loop robotic arm and daisy chain the CAN bus. So that is kind of similar to the project that Jan had presentation about. So closed loop control of DC motors with current sensing, so you can detect forces and torques. I kind of decided to do this gripper because there is nothing on the market that you can buy for some cheap price, and there is no open source project. So you can buy a force gripper for like $3,000, and that is out of budget for most DIY and open source projects. So this uses linear potentiometers for speed and position control, current sensing through the shunt, and everything is like tightly packed inside this gripper housing. And this is like, I believe, 100 millimeter in length. So it is really, really small. It also communicates with CAN bus or UART, so you can really easily connect it to previous robotic arms and just daisy chain with the motors. Another thing I was not really happy about the previous projects is that the Ginter is really ugly. And so I saw a modern Ginter library that I used to build this new software, and I kind of cleaned it up from the previous versions, so everything is more sleek. There is no unnecessary buttons or details, and it has a programming interface, jogging interface. You can also change the like dark mode, light mode, export programs and stuff like that. And it is kind of inspired by some classic industrial robot interfaces. There's some questions.
Yeah, Peter, that is fantastic. I gotta tell you, I was so excited to see that you applied to be on the showcase. I've been following your project for the past few months since you posted it on Hackaday most recently, but it's cool seeing even the progress that you've made since then. So yeah, I guess someone was asking, what are some good like robotic simulation softwares that you used when you were making this?
I did not. So everything is like brute force. Really fan of ROS, and only simulator I use is the like built-in in the robotic toolbox from Peter Cork, and that is like enough for me.
Okay, sounds good.
Yeah, I'll also say very, very impressive. It's easily one of the very best do-it-yourself robots that is available in the community. And again, it's nice. Something I think I've learned over the last few years is that the robotics scene in Poland is underrated and underinvested in. It's clearly a consistent theme now. I've seen quite a few robots over the last few years that are really, really good. So you talk about the next version of the robot you're going to is smaller, more compact. It looks like it's got a smaller workspace but more precision. Is that right?
Yes. So it will be like much more precise and much more faster. I sadly don't have any videos of it because it's still like in the progress. But the biggest downfall of like all those DIY robotic projects is just a really weak gearboxes in terms of precision, because that like kills your whole project if you're aiming to do anything serious. So like easiest solution is just to buy something off the shelf and spend a little bit more money on that and just do it that way. And in terms of the build of the range and the size of the robot, I believe that is like enough for most of the stuff people plan to use these robots, because like a 15-kilo robot is really clanky and hard to carry, and it's even dangerous if you don't have brakes on the servos or BLDCs, and I know it's not really safe to play with that, and you can't really then increase speeds because you can hurt someone, or so it's not really worth it. And
that's a really good point. Of course, one of the issues with open source robots is you can't sue them if you get injured by it. So it's really good for you to think about what is safe and viable for people to use, rather than just building the biggest, best thing possible that someone can then hurt themselves with.
Yeah, and I'm even planning to put brakes on this robot, even though it is small. I believe that will like improve the usability and just improve this robot in general. So yeah.
Nice, yeah.
Yeah, really.
We do have one question from the YouTube chat, which is someone said you mentioned the minimalistic stepper motor controllers that bolt onto the back of stepper motors. Do you have a source for ordering those, or did you just design and build those entirely yourself?
Built by me, and I believe they will be available for sale. I will post like links to my Discord channel and GitHub and I don't know, Instagram, so people can contact me. But yeah, they will be available for sale. And I know I had the first intention for them was to just be like to be able to make that new robotic arm closed loop, but I also added the direction and step interface CAN and UART and everything, so you can just in theory it should be able to control printers, so closed loop printers, and it will be able to run like through FOC on steppers, unlike those AliExpress stepper drivers that you can like plug on the steppers. They don't run through FOC, and I don't know if that is really important for the printers, but if people want to play with spots on stepper, they should like build something like this.
Yeah, fantastic. Please do share that link. Yeah, I'm sure people will be really interested in seeing that. One kind of final thing just for me, I know that one of the biggest limitations with building, very precise like home-built DIY robot arms is it's hard to make them as rigid as they need to be to really maintain that level of precision. And I've been really interested seeing, we're seeing more services where you can order, machined aluminum and steel and laser cut aluminum and steel. Would you ever consider integrating laser cut metal parts into your robots, or are you going to stick entirely with, everything is either off the shelf or is 3D printed for your next, robots?
Oh, we can't hear you. Sorry, the start of your question was muted. Sorry, the start of your answer, Peter.
Oh, okay. So the problem is that most 3D printed robotic arms are built to be made on 3D printers. So if you want to make them with like CNC cut aluminum or even casting, you will have really hard time doing that, because it's just like it doesn't work like that way. So you need to design parts to be made on the CNC machines. Like some parts on the new robot can be made on a CNC, but it doesn't bring like any benefit if just like few parts are built. Some you need to build mostly those upper arm, forearm parts that will carry most of the stress and where the motors will connect. So a real big problem with also other 3D printed robotic arms on the DIY community is that they mess up the connections between the motors and the plastic parts. They usually make them really weak, and like just like they slide shafts inside a plastic part and it will just slip. It doesn't work that way. So you need the metal couplers or something like that to fit on the plastic parts. So there is actually a possibility to like machine couplers and stuff like that. That is a great idea, but to machine the whole robot is it's not really like a good idea.
Okay.
So you would say that we're still a few years away and a few generations of robot arms before it makes sense to be going beyond 3D printed and off the shelf. I mean, there will come a time where it makes sense for do-it-yourself arms to have, you know, incorporated metal 3D printing and stuff like that. But right now, where the technology is, it doesn't quite make sense. Would you agree with that?
Yes, I mean, I believe the same thing with the arms will happen as it did with 3D printers. So it's some one design will like reign over all, and it will be like highly copied, and then it will just be like avalanche effect, and everybody will start to like innovate and rip apart that design and just make it better, and like it will lead to more innovations. But yeah.
So I guess you're hoping then to be ready then for when the time comes to have I guess a position in the market, the same way that Joseph Prusa did for 3D printing. You want to be there for robot arms.
I hope so.
I think you probably will be, based on the quality of your arm. I think you probably will be. Right, well, I think that takes us to the end of our first session for this morning. Peter, please do post a couple of links in the chat to your work before we sign off for the morning, as it were. And Michael, could you bring us up, remind me of the time for when we return then for the afternoon?
Yeah, of course. So we are returning this afternoon at 2 p.m. Eastern time in the US, and our keynote presentation is going to be the CEO of Viome. So if you're interested in seeing any of their work or asking him any questions, please sign on. We have a wonderful keynote planned, and we have a lot of really, really amazing robots from the community that we're going to see this afternoon. So we'll see you all then. Enjoy your short lunch break, and we'll see you soon.
Yep, hope to see you back for the afternoon. Keynote is really fascinating, one to definitely stick around for. In the meantime, do feel free to share on social media for the event if you wish to. Otherwise, thank you very much, and we'll see you in the afternoon then. All the best. Cool. I've ended now the live stream, and now we're going to end